So, today we're diving into one of humanity's greatest engineering achievements, these massive offshore platforms that are basically cities out in the middle of the sea. These things stand against the full, raw power of the ocean, all to power our world, and we're going to figure out exactly how they pull it off. It really all starts with a pretty basic question. You look at a colossal structure like this one, the Transocean Enabler, and you just have to wonder, how does that even exist? How can something that huge operate safely for decades in what is, without a doubt, one of the most violent and unforgiving environments on Earth? Well, the short answer is because of this. Our planet's relentless and growing demand for energy. Just look at this chart. The world is burning through well over 80 million barrels of crude oil every single day. And that incredible thirst is what drives us to push the absolute limits of engineering to go find and extract resources from the deepest, most remote corners of our oceans. To really get a grip on how this is even possible, let's take a little journey. We'll start from the coastline and head way out into the deep sea, and you'll see how the technology has had to evolve to meet the challenge of deeper and deeper water. Okay, so basically, all these offshore platforms fit into one of two big families. On one hand, you've got fixed platforms, and just like the name says, they are physically anchored right into the seabed, solid. Then you've got floating platforms. These guys are moored in place with gigantic chains and cables, but they're not rigidly stuck to the bottom. They have a little give, letting them move with the ocean. And that one fundamental difference, well, it dictates everything about their design. And this right here, this is basically our roadmap. As we move from left to right, from the shallow waters near the coast, out into the abyss, you can see the platforms get way more complex, and the engineering honestly becomes truly mind-bending. So, closer to shore, in waters up to about 400 meters, the absolute workhorse is the jacket platform. The easiest way to think about it is like a giant steel scaffold, almost like the foundation of an underwater skyscraper. It has these long legs that are piled deep into the seabed, creating this incredibly rigid and stable base for everything on top. But once you get too deep for a fixed base, you need a totally different and kind of counterintuitive approach. Enter the tension leg platform, or TLP. The engineering here is just brilliant. See, the platform is naturally buoyant, so it wants to float up, right? But it's tethered to the seabed with these super tight steel tendons that are constantly pulling it down. It's that tension that holds the platform incredibly steady, making it a stable base for drilling in water over 2 kilometers deep. It's wild. And then, for the most extreme depths, we've got the Spar platform. And the concept behind it is just beautiful in its simplicity. It's basically a massive, deep vertical cylinder, kind of like a giant fishing bobber. Most of its mass is way, way below the surface, where the water is calm, and that makes it unbelievably stable against all the chaos from the wind and waves up top. It just goes to show how a simple principle of physics can conquer the most challenging environments imaginable. So just how deep are we talking about here? Well, the world's deepest platform, the Perdido Spar out in the Gulf of Mexico, operates in 2,450 meters of water. Let that sink in. That's almost 2.5 kilometers, or 1.5 miles straight down. That kind of scale brings with it some truly unimaginable forces. Right, so operating at these insane depths means you're up against forces that are just hard to even wrap your head around. It's not enough to build something big. You have to engineer a structure that can literally win a constant, decades-long fight with the ocean itself. Which brings us to the absolute heart of the engineering problem here. How, in the world, do you design something to survive in an environment that is actively and relentlessly trying to rip it to shreds? Well, you start by planning for the absolute extremes. These platforms are designed from day one to withstand sustained hurricane-force winds of 170 kilometers per hour. And then you've got the waves. In places like the brutal North Sea, the design wave, that's the monster wave the platform absolutely has to survive, can be over 32 meters high. Yeah, you heard that right. That is taller than a 10-story building crashing into you. And they have to put up with this stuff not just for a day or a week. They have to endure it for a minimum lifespan of over 25 years, all while sitting in corrosive salt water that is constantly trying to weaken every single piece of steel. So to survive all this, engineers have to account for every possible force. They start with what they call dead loads. That's just the massive weight of the structure itself. Then you add the live loads, all the movable equipment, the people, the supplies. Then you pile on the colossal environmental loads from those hurricane winds and giant waves. And finally, you have to model the dynamic loads, those constant, repeating forces that try to fatigue the steel over millions and millions of cycles. You obviously can't just build one of these things and hope for the best. Trial and error isn't an option. The only way to succeed is to build it and break it thousands of times in a virtual world before you ever cut a single piece of steel. This is the age of the digital blueprint. And that brings us to this incredible concept of a digital twin. On the left, you've got a super detailed computer model of a platform, and on the right, the real thing. I mean, every single beam, every bolt, every weld is modeled and then virtually slammed with simulated storms and stresses to make absolutely sure it will survive in the real world. And this is all possible because of an amazing digital toolkit. To figure out how every single weld is going to handle stress, engineers use software like ANSYS. To simulate the impact of those 30-meter waves, they use powerful hydrodynamic tools like OrcaFlex. And it's all brought together in these incredibly detailed 3D models using programs like AutoCAD and SACS, building that digital twin piece by painstaking piece. Okay, so let's bring this all home. How does that digital blueprint become this real-world titan of the sea? And more importantly, how is this incredible engineering legacy paving the way for energy future? The journey itself is just monumental. It all starts with that digital design. Then comes fabrication, where these enormous pieces are built in coastal shipyards. These sections, weighing thousands of tons, are then hauled across entire oceans, installed and assembled out in the open sea, which is an insane feat of marine engineering all on its own, before finally being brought online for decades of service. And here's the really cool part, where it all comes full circle. The decades of knowledge we've gained from designing these platforms, understanding the hydrodynamics, the mooring systems, how to just survive out there. All of that is now being directly applied to the next generation of energy, floating offshore wind turbines. The very same solutions that unlocked fossil fuels from the deep are now being repurposed to harvest clean energy from it. There's no doubt about it. These immense structures were among the defining engineering marvels of the 20th century. Which really leaves you with one final thought. What new marvels, built on this very legacy, will rise from the sea to power the next one?